What we're going to do now is we're going to talk more systematically about how to implement a concurrent collector. And what we're going to do here is we're going to implement a concurrent collector that's going to work on concurrent maps. So it's going to be a concurrent map collector. We've talked earlier about implementing a concurrent set collector. Now we're going to have a concurrent map collector. Now, just to kind of talk through some things that I mentioned earlier, but this is a more systematic way of talking about this. The Java collectors utility class, that's the one we've seen before that gives us things like maps and sets and so on, and lists, has all these factor methods that make non-concurrent collectors. Here are some examples. It also has a handful of methods that make concurrent collectors. So there's a set of methods to make a concurrent collector for a map, and you can also have a concurrent collector for a skip list map, which I've never really used, but it's another thing you can use that is another way to optimize the performance of collections. However, there are no predefined concurrent collectors that Java provides out of the box that create sorted maps. So Hashmap isn't sorted, a skip list is not sorted. There's nothing that makes sorted maps. And sometimes you want sorted maps. And in fact, we're going to look at an example that leverages sorted maps quite nicely. So to overcome this problem, I defined a concurrent map collector that supports collection into sorted maps. And we'll take a look and see how this thing works. It's in another example that's shown here in the EX37 folder in my Java 8 package. It takes some interesting parameters. It takes a supplier, and this is used to customize the type of map returned from the collector. So most commonly, it would be something like a tree set map, which will be sorted. And in fact, it uses a very, very, very clever scheme internally to make all this stuff work efficiently. The concurrent map collector defines 4 generic types. Type T, as always with these collectors, is just the type of objects that are available from the stream, which could be a simple immutable entry or a simple entry or a GCD param or whatever we want. K is the type of key used in the map, which could be a string or a double or something else along those lines, a long, for example. V is the type of value used in the map, which could be an integer, search result, GCD result, again, whatever we want to make via the results. And M is the type of map that's returned from the collector. And it could be a concurrent hash map, a tree map, a linked hash map. Internally, the implementation of concurrent map collector uses concurrent hash map. And the reason for that is that's super optimized for concurrent access. So it makes sense to make that the mutable result container for this particular implementation. And the clever thing that we're going to do here is we're going to use the concurrent hash map internally to speed up the way in which the elements are added. And then we're going to have this final type M, which will be the actual type returned from the collector. Now, as I mentioned before, there's already collectors that are concurrent hash map collectors and skip list collectors, but we want to be able to do ones that are sorted. So tree map would be a good example of that. There's a factor method defined on the concurrent map collector that makes a new instance of the concurrent map collector that's parameterized by whatever types we want to use for these various things. And we'll talk about what those types are. For example, as we'll see, you can make, or it implements it by saying concurrent map collector, passing in the key mapper, which is a function, a value mapper, which is a function, a merge function, which is a binary operator, and then finally the map supplier, which is a supplier that makes the appropriate type of map that we want to use as the return. So we have 5 key methods that are defined in concurrent hash map collector. Characteristics is what's used to give metadata about the type of collector. So we make it unordered because it's concurrent, and we make it concurrent. And what concurrent means is that the accumulator, the type that returned from the accumulator is called concurrently on the concurrent hash map mutable result container. That should be mutable, not multiple. There's only one of them, so it's mutable. It's one mutable result container. And as you'll see, concurrent hash maps method, which is what's used here as the mutable result container, are all synchronized. And it's synchronized in a super duper optimized way that we've talked about before, where it's able to allow multiple read operations on the concurrent hash map to all go in parallel. And if you have multiple write operations on the concurrent hash map, when you put something in the concurrent hash map, for example, as long as they don't hash to the same location in the hash table, those will go in parallel. And even if they hash to the same location, there's some clever ways to make the updates as optimized and as contention-free as possible. And here's what we do. We just return a set of these characteristics for concurrent and unordered. The supplier returns a supplier that's going to act as the factor method to generate an empty mutable result container. In this case, it's going to be concurrent hash map : new. That's the constructor reference for concurrent hash map. The accumulator returns something called a by consumer that'll be used to add a new element to the existing concurrent hash map. And this is what this method looks like. And this is a crazy, wacky method, but it's necessary to handle the semantics of merging items in a hash map. So if you have two keys that hash to the same location, the question is, what happens? And you can define that by passing in a merge function. In our case, we don't care because these are Shakespeare words, and one anon is as good as another anon. And so as a result, we just pick one, and we don't really care which one it is. So here's what the accumulator method looks like. We call the merge method on the map, and we go ahead and make a new key item from the element. We make a new value item from the element, and then we pass in the merge function, which will figure out what happens if they end up hashing to the same value. Concurrent hash map's merge method is synchronized efficiently, so you can read more about that down here. The combiner returns a binary operator that merges two result containers together. This would be a classic example of doing this. We take all the elements in one container, for example, all hash map elements, and merge them at the end of the other one. For parallel streams, again, keep in mind this is a no-op. And then finally, the finisher returns a function that will convert the concurrent hash map into its final result type if necessary. It may not be necessary to do that, but if it's necessary, it'll do it. And as you can see here, it only copies the data if the map that we're collecting into is not a concurrent hash map. If it is a concurrent hash map, we've already got it in the format we want, so we'll just hand it back. But if it's some other type of map, such as a tree set or a tree map, in this case a tree map, then we'll go ahead and make a new tree map, put all the elements from the concurrent hash map into it, which will do the sorting, and then we'll return that new map, that new type of map. So the cool part about this is the internals of this whole implementation of the concurrent map collector use concurrent hash map because it's super optimized, but then it can transform it into another type of map at the very end to get the sorted semantics if that's what we want to have as the results. So here's the actual implementation, and we'll go take a look at this in just a second.